Hi, and welcome to video 2.4a, the introduction to the chain rule. So, up till now, we have done the derivative of x to the third power is 3x squared, x to the 1/2 is 1/2 x to the negative half. But what we've always had here was just plain pretty little 1x. What's going to happen with the chain rule is we're going to be finding the derivative of composite functions. So, it didn't matter what the exponent was as long as it was a constant, any real number, but what we've been dealing with is a base of just plain old x. So what happens if we have something uglier than just plain old x? Let's say we have 4x squared plus 7x all cubed. So what happened, of course you could cube this, which you would not want to do, and certainly if it was to the power of 32, I definitely would not want to expand it. So we're going to look at it as the derivative of an ugly quantity. Ugly is anything other than just plain old x cubed. Now, really what you can do is you can look at this as a composite function, because this is the cube of 4x squared plus 7x. So if you let g of x be 4x squared plus 7x, and you let f of x be x cubed, in other words, the inner function is your g of x, and what you're doing to that inner function is your f of x. You can see that your f of g of x, your composite function, is f of g of x, which is 4x squared plus 7x, and of course f of something is the cube of that something. So the way we deal with this is, like before, if you had something to the cubed and you wanted to take the derivative, you would go 3 times that something squared. But because that something is not plain old x, you will also have to multiply that by the derivative of that quantity. So here is the actual chain rule, and you do need to know this formula because they will give you numerical questions where you won't have algebraic functions to deal with. So the chain rule says that the derivative of a composite function, f of g of x, is equal to the derivative of the outer function evaluated at the inner function times the derivative of the inner function. What it is not equal to is the derivative of f at the derivative of g. That's not what it's equal to. Okay, so here's an example. If you have the derivative with respect to x of our 4x squared plus 7x all cubed, the example we had up there, is going to be 3 times this ugly thing squared times the derivative of that ugly thing. So it's the derivative of the outer function evaluated at the inner function times the derivative of the inner function. Now, if I just rearrange it a little bit here, that's all I did. I didn't do anything very much more exciting than that. Other than the fact that there is a common factor of x here. If you factor it out, that's x squared times 4x plus 7 all squared, and you can see there's 3x squared. Okay, what it is not equal to, which some of you will do, and I can't give even any partial credit, is you'll realize that you're differentiating the cube of something, and you'll know it's 3 times something squared, and many people will just put the derivative of the inner function here, and that is not what it is. Okay, so the derivative of ugly cubed is 3 times ugly squared times the derivative with respect to x of ugly. Okay, so here it is again. Now here it is with 3 of them. So the f of g of h of x. So there's an outer function, a middle function, and an inner function. So you start with the outside. It's f prime of this extremely ugly thing times, and then you go to the middle one, g prime of whatever it is, times, and finally the derivative of the inner function. So here's an example. Whoops. Okay, so if we have the following, the derivative of tan cubed of 4x plus 1. So the first thing you're going to want to do is understand when we say tan cubed, just like here when we say sine squared x, we mean the square of sine x. If it's written as the sine of x squared, it really means only the angle is squared, which is kind of a weird thing to do anyways. So the first thing we do is rewrite this as the cube of the tan of 4x plus 1. So you want to get into understanding the outer function is the cube of, the middle function is the tan of, and the inner function is the 4x plus 1. So we do the outer function, which is blah, blah, blah cubed. The derivative of blah, blah, blah cubed is 3 times blah, blah, blah squared. Then inside here, since this is not pretty little x, you have the derivative of the tan of blah. So the derivative of the tan of blah is the secant squared of blah. And then finally you have an inner function, 4x plus 1, and the derivative of that is 4. And then we pretty it up, 3 times 4 is 12, and then I'm just rewriting it. Okay, so still chain rule. So here's another example. You know if you have y equals x squared, it'll be 2 times x to the power of 1. And really, you could do the chain rule on this, even though it's pretty little x, because the derivative of x is 1. So right here, we're going to have 2 times the ugly thing to the power of 1 times the derivative of the ugly thing, and there is your answer. Here's another example. This is very simple. This is just as if you had this. If you had the derivative of 3 times x to the 5th, you'd do 15 times x to the 4th. So here you're going to do 15 times the ugly thing to the 4th, and of course, because it's ugly, times the derivative of the ugly thing. And then we just rewrite it. Here's number 30. So you could look at this in different ways. I think I'm going to go this route, which is I'm just going to leave this as a quotient, and then I have an extremely ugly thing squared. You could actually square the numerator and denominator and then do a quotient rule on this. When you go to take the derivative of the denominator, you will be dealing with the chain rule. Or from here, you could rewrite it as times the denominator to the power of -2. Now you'll have a product rule, and of course when it comes to taking the derivative of this, let's see if I can move that over a bit. Let's move this, I'm going to move over. You'd end up dealing with the product rule, and here when you go to take the derivative of this, you would have to use the chain rule. With a negative exponent, probably not worth your while. Okay, so this one method right here, I'm going to do, this is something squared, so I'm going to go 2 times the something to the 1, and then times the derivative of that something, which is, of course, a quotient rule. Okay? And then you'll expand all this and simplify it to get this expression here. You'll factor, and you'll give a single simplified factored fraction. Make sure it's h prime of t. Do not assume it's always x. Plus, if you keep writing t, how could it be x? Now, this has got a few things going on, because this is the square root of an ugly thing, so there'll be a chain rule here, but there's also a product rule. So I would suggest putting parentheses around the 1/2 x squared and parentheses around the rewritten 16 minus x squared to the half. So here's your product rule. When you get to the derivative of this one, you'll have 1/2 times the ugly thing to the -1/2 times the derivative of the ugly thing. So I'm rewriting this first term. Okay, I'm bringing this down here and multiplying the x by the x squared, and I have, this 2 cancels with this 2. Alright, and then this term here, I'm just leaving it as is. Now what I did here, and there's many different ways to proceed, is I found a common denominator, so times 1 times 1 times 2 times 16 minus x squared to the half. So there's the 2, there's the x from here, and of course 16 minus x squared to the half times 16 minus x squared to the half is 16 minus x squared. You will then distribute, simplify, try to factor. It doesn't factor. The denominator factors a little further. It is 16 minus x squared, but that's not really necessary. In 37 through 42, use a computer algebra system to find the derivative of the function, so you know how to do that. Then use the utility to graph the function and its derivative on the same set of coordinate axes. At this point in time, let's not worry right now about describe the behavior of all of this, because we're going to get to that later. Okay, so don't worry about that for now. Alright, so I'm actually not going to do any of these. I can let you look at them. 37 through 42 is down here, okay? Obviously, they all involve some kind of a chain rule, but it really doesn't matter because you are doing it all with the calculator. So, you know, there's a chain rule here because it's the tan of an ugly thing. This is the cosine of an ugly thing. The square root of an ugly thing, same thing, same thing, same thing. Don't really know why this one's here. Yeah, 37 is an old thing. Okay. 45 to 66, if we look at those, find the derivative of the function, and now, of course, you'll notice none of these had trig in them, and all of these have trig in them. So they're simply chain rule with trig is the only thing. So we have y equals the cosine of 1 minus x squared. This really, the square is not for the cosine, it's just for this angle. So the outer function is the cosine of, the middle function is the square of, and the inner function is 1 minus 2x. So your derivative, which is written one of these ways, there's no f of x, so you can't say f prime of x, would be the outer function is the cosine of a thing. The derivative of that is negative sine of a thing. Then the middle function is the square of something. The derivative of the square of something is 2 times that something to the 1. And finally, your inner function is 1 minus 2x. The derivative of that is negative 2. And then we just kind of simplify. And that's the end of video 2.4a.